Saxon Advanced Mathematics, Lesson 25. You guys, we're going to review two types of word problems today. The first one is age problems. We did these at the end of last year, Algebra 2, and the trick to these is how we set up the variables. So let me read you the story. We're only going to do one of these. I think it will come back to you quickly. 10 years ago, Thomas was twice as old as Patricia. 5 years from now, Thomas will be 10 years older than Patricia. How old are both people now? So what we do is we set up a table to organize our variables. We've got Thomas and we've got Patricia. I'm not even going to bother writing out their names. Okay, so we've got 3 time periods to look at. And I'm going to put them in order chronologically. The 3 time periods are 10 years ago, now, and 5 years from now. And my words are going to go out of the box and I don't even care. All right. We start by setting the variables for now. Is his name Tom? Thomas. Thomas now. Whoops. Patricia now. Okay. 10 years ago, it was Thomas now minus 10. Patricia now minus 10. And 5 years in the future, it'll be Tom now plus 5. Patricia now plus 5. This is the secret to doing these problems because now we're setting up all these variables just based on one for each of them, right? And we've just adjusted those by time frames. All right, 10 years ago, Thomas was twice as old as Patricia. Okay, so we're dealing in the 10 years ago, and we know that him 10 years ago was older than her 10 years ago. So first I write an inequality. Let me read it again. 10 years ago, Thomas was twice as old as Patricia. Okay, so he's older. Somebody's got to get multiplied by 2. And even though it said he's twice as old, we can see he doesn't need to be multiplied by 2. She does. And that will make it equal, and that makes sense. And if you think about it, if he was 80 and she's 40, then he's twice as old. You have to multiply her to get them to equal. Okay, so this is our first equation. The second one says 5 years from now, okay, so we'll use these variables, Thomas will be 10 years older than Patricia. So in 5 years, he's still going to be older than Patricia. He'll be 10 years older. So again, we can see we either subtract 5 here or add it here. I always like to put it down here. So to make them equal, she's going to need the extra 10 added because he's older than her. We need to make them equal. All right, and now we are ready to solve this as a system of equations. The first thing we want to do is simplify each equation and see what we get. Okay? So I'm going to start by cleaning up A. And I could have left myself more space and cleaned them up as I went, but that's okay. I'll do it this way. Tn minus 10 equals 2pn minus 20. All right? And then I'm going to add, I'm going to rearrange these the way we usually do systems of equations, where I'm going to do Tn plus or minus Pn equals plain number. So I'm going to kick the plain number over here, and I'm going to swim the other age over there. And this is how it will look when I'm done. That cancels, so I'll get Tn minus 2Pn equals minus 10. And then I will get, so this is my new A. This is the one I like. And then this one, I'll do it over here so that I can write them together. Tn plus 5 equals Pn plus 15. So I'll subtract 5 and I'll subtract the Pn. Those cancel, those cancel. Tn minus Pn equals 10. All right, so and that's my other one. I'm gonna bring this one down here and write them together. All right, there they are. New and improved. Now, what do I want to do to change these? All right, I look down the columns. I can see that my TNs need the signs cleaned up, but they have the coefficient of 1, both of them, so that would be relatively easy. This one, I not only have to change a sign, but I have to multiply. So let's just multiply the top one by -1 all the way across. Then I'll write it down here, and it'll be nice and easy. All right, so this becomes minus Tn. This turns into a plus 2Pn equals, and that becomes a positive 10. Make sense? Now I add them. These cancel. This becomes Pn. Ooh, I like. All right. So if she's 20, then I need to plug this back in to one of my equations and get the age of Thomas. Let's see, I can plug it back into this one, right? So that Tn equals Tn minus, let's do this one. This one's better. Tn minus 20 equals 10. Add 20 to both sides. And I get, I'm going to write it here, Tn equals 30. So those are their ages now. Patricia's 20 and Thomas is 30. Yay. Correct and correct. All right? The whole trick in these is setting the variables up, getting the equations correct. I mean, that's not the hard part. This is the trick of the whole thing. This is pretty typical drama. And then the way you always have to clean up these equations first before you can eliminate them very well. So that is a great example. I hope that is enough to get you going. We're now going to direct our attention to these rate problems that are honestly a whole lot trickier. All right. We've talked a lot about how distance equals rate times time, right? If you're traveling in a car, you multiply the speed of the car times the times you traveled. And that works out beautifully. But sometimes we're measuring things with rates and times that don't give us a distance so much as they give us what we call a job. All right? So this is like in our first example, we've got people washing cars. And they've got a rate of how quickly they wash the cars. And, hi Grace, my daughters are getting the dog all riled up and she is aping around. It's really funny. The rate of washing cars times the time they wash cars will tell us how many cars they can wash. So we're taking this concept and we're just kind of fine-tuning it to a slightly different context, okay? So, and these problems are tricky, you guys, so be patient with yourselves. Each one's a little different too. Joe Frank can wash 3 cars in 5 hours, and Meryl can wash 4 cars in 3 hours. 15 cars need to be washed. If Joe Frank works for 2 hours and is then joined by Meryl, how long will Meryl and Joe Frank have to work together to finish washing the cars? Yikes. That's a lot, isn't it? So we've got Joe Frank working by himself, and then we have Joe Frank plus Meryl, and together they have to do 15 cars. All right, so they have rates and times. We've got some information about the rates. But what we want to do, we can think of that as changing, but we can also think of it as adding, right? Him by himself plus them together, that's the whole job. So what we want to do first is figure out how much can Joe Frank do by himself. It says Joe Frank can wash 3 cars in 5 hours. Aha! The rate of Joe Frank equals 3 cars for every 5 hours. And I'm just going to go right ahead and write the words as part of that, because we can deal with that. That's fine. And it tells us in a minute, oh, well, let's do the rate of Meryl. She can do 4 cars in 3 hours. I'm just going to double check and make sure I got that right. 3 cars in 5 hours. 4 cars in 3 hours. Meryl's way faster, right? All right, 15 cars needed to be done. So that's the job, right? It's like the distance. It's the finished product. If Joe works for 2 hours here and then is joined by Meryl, how long will they have to work together? That's our question, to finish washing the 15 cars. Let's figure out how many cars he's going to wash in that 2 hours he works by himself. That will be the rate of Joe Frank times the time of Joe Frank will equal the cars of just Joe Frank. His rate is 3/5 cars per hour. I'm going to keep that in there to make sure I'm making sense. The time is 2 hours. So that means if I multiply those together, the hours cancels and I get 6/5 cars. What? Okay, what does that mean? That means he'll finish 1 car and he'll be 1/5 into the next car. That's kind of weird, isn't it? That seems odd. But what it tells us is that of the 15 cars that they have to wash, he will have finished that many. So what will be left? 15 minus 6/5. All right, let's change this into a fraction with a 5 on the bottom. That would be what? Sorry, I'm getting distracted. This is 75/5, okay? If we put the number of cars they have to wash in a fraction with a 5 on the bottom so that we can compare these, 15 equals 75/5. Joe Frank's doing this many by himself. That means that's how many cars they have to do together. Okay? So what that means is that the rate of Joe Frank times the time they work together plus the rate of Meryl times the time they work together has to equal 69/5 cars. What? Does that make sense? And this is the time together. And I'm just using a plain T to solve for that, right? So we have their rates separately. They're right there. We don't know the time, but that'll be the variable. And the job that they have to accomplish is the cars that are left after Joe Frank does his little beginning thing, right? So we figured all that out first. And now we know how much of the job is left. Okay, so now what we can do is substitute in their rates and we'll be ready to solve. This is hard, you guys. This is hard. Okay, so 3/5. And I'm going to go ahead and I'm going to keep putting the letters in. Times T plus 4 cars over 3 hours times T equals 65 over 5. Oh, I'm sorry, 69. My bad. I just copied wrong. Okay? It's one of those moments when I think, oh, I know what you're thinking. You're all like, what is she doing? Why did it change to 65? Because I went a little wild. All right, so here we have and this should be cars, right? So these hours hopefully are gonna cancel out and we're gonna get it, the units will work out right too. Sometimes the units help me track with the story a little bit better. They make me feel like it's making sense when they start to cancel. So we'll see what happens. You don't necessarily need those in there. All right, I want to blow up these denominators. We've got 5, 3, and 5. That means I multiply everything by 15. Remember, this is the way I like to do that. All right, these cancel, and I'm going to get 3 times 3. These cancel, and I'm going to get 5 times 3. These cancel, and I'm going to get 3 times 69. That'll be interesting, won't it? Okay. So now, this will be 9 cars per hour times the time. I'm going to put parentheses around that because otherwise it looks really confusing. Plus 20 cars per hour times the time equals, and what's 69 times 3? Let's do that. 27, 207. Does that make sense? So now we can add these together and we get 29 cars per hour time equals 207. This would be cars, right? I haven't been writing that, but we can add that back in because that's the job. And so now I'm going to divide by 29 cars per hour. Right? Remember, okay, so my number, I'll tell you right now, my number is prime. It's not going to go anywhere. So this is done, the number is done. But let's treat the words like a complex fraction. To make the denominator go away, I'm going to multiply by the reciprocal. And then I'm going to have to do the same for the top. Now this goes away, the cars cancel, and I get, wait, this whole thing. There's my answer. 207 over 29. What a meaningless number. Hours equals the time that they're going to need together to work. Woo! I would have liked that so much better if it would have come out to a nice number. I liked seeing the units cancel. I liked that I could kind of make sense of it, that I calculate this first chunk and then subtract that from the total job and then use this as my base equation to do the rest. But the numbers got a little crazy. That wasn't satisfying. Let's try another one that will also have unsatisfying numbers. How's that for a nice lead in, right? These rate problems are tough because every one has its own weird wrinkles and you have to sort it out. All right, if 5 workers can do one job in 8 days, how many workers would it take to do 3 jobs in 7 days? It's crazy, right? All right, this one is different because instead of just doing rate times time equals the job, we're saying rate times time times the number of workers we can vary will equal the job, okay? So this is a kind of a new, more refined way to do this if we want to mix up the number of workers, and we're assuming they all work at the same rate. That's what we're assuming in this. So if 5 workers we want to find the rate of these workers, okay? So we know that we've got 5 workers can do one job. Oh wait, I'm sorry. Let me approach that differently. Here's our formula. We want to find the rate of these guys. The rate we can find as being equal to the job divided by T times W. We basically can solve this as an abstract equation by dividing by T and W, and we get this, right? So this is just that rearranged. Now we can find the rate of these guys. The rate is equal to 1 job for every 5 workers in 8 days. So it's 8 days times 5 workers. Okay, so all we've done is taken this basic equation, rearranged it to get the rate by itself, plugged in the information from our story, and now we're going to refine it one more step. 1 job for every 40 worker days. I just multiplied those 2 together, all right? Now we've got our rate. How many workers would it take to do 3 jobs in 7 days? So now we can use this in this form. What did I say? How many workers would it take to do 3 jobs in 7 days? Okay. Now that we've got our rate, so step 1 was solve for the rate, and step 2 is use the rate to answer the question. All right, so there's our rate. And now we want to know how many workers it's going to take to do 3 jobs in 7 days. So we use this formula again. Our rate is 1 over 40 worker days. I'll put that in, 1 job for every 40 worker days, times the time, we have 7 days, times the number of workers, well, that's what we're solving for, equals how many jobs? 3 jobs. Okay? So, what we want to do is solve now. Okay? And we're going to solve the words and the letters. Woo! We are wild. First of all, I can cancel out days and days, can't I? And what I'm going to do to isolate this W is I'm going to multiply it by the reciprocal of what I've got here. So I can see, here, I'm going to put my reciprocal in here. It's going to be 40 on the top, 7 on the bottom. This is going to be 40 workers for 7 and the jobs is the word. I'm not trying to make sense of this. I'm just letting my words follow, right? So this will cancel, and this will cancel. And then over here, I multiply by 40 over 7. And this is workers. Here, let me write it down here. I'm running out of space. It'll be W, the number of workers, equals 3 jobs. That's what was already there, times 40 workers divided by 7 jobs. All right? Again, I am not trying to make logic of my words. I just put them where they made sense in the beginning, but now I'm just letting them algebraically follow along in the process. Notice that jobs cancels to jobs, and I'm left with workers, which is exactly what I want. So I know that my numbers all behaved properly. That's why I track the words, you guys, is it helps me make sure that the numbers are going where I want them to go, because the units should all cancel out until I end up with what I want. And so the number of workers equals 120 over 7. What in the world? That's the final answer. If you grab a calculator or take the time, you'll find out that that's 17.14. So somebody's going to have to chop up a worker. Just kidding. But this answer is perfectly fine with me. That's correct. All right. Whew. That was rough. That was rough. If you can follow along, I'm quite sure that the problems in the homework will fit these models really well. So you can come back to your notes, or you can look in the book, because these examples, I'm working them just like John does. But you can follow this same process and make it fit to the example you have. But there was the one about the washing the cars where somebody works by themselves. This is the one where we expand the formula to have workers, and then the next one is going to be similar to this in that we're going to have a slightly expanded version. So let's flip to that. This is the last problem for this lesson. And let me just write this up here. Rate times time times the number of workers equals the job. Example 25.5. This is one of my favorite all-time problems. Mary had 252 gallons of milk. I'll write it out. This would feed 42 infants for 12 days. All right. If we use this information, we can figure out what rate these infants are sucking down this milk. Let's see if that's going to help us. Then 14, so after this, 14 more infants were placed in the nursery. And 48 more gallons of milk were provided. How long would the milk last now? Wow, okay. The first thing we have to do is adapt our formula to take into account the specifics of our scenario. The rate at which they drink times the number of days which they're drinking it times the number of infants that we have will determine how many gallons of milk we need. So I'm taking the particulars of this story and shaping them to fit this format. Their job is to drink milk, and so they're measuring their job in gallons. The rate, which we'll have to figure out, times the number of days, times the number of infants, drives how much milk they drink. So to find the rate of the gallon, of the babies, we'll divide both sides. So the rate will equal the gallons divided by days times infants, right? I'm just algebraically playing with that. So that means we can use this information. This is our step 1 to solve for, solve for the rate. We rearranged it algebraically. Now we can plug in the rate equals the number of gallons, 252. And again, I'm going to write my units up because that'll help me make sure I'm doing this properly. Divided by 42 times 12, which I'm pretty sure is 504. Infant days. Good Lord, right? That's crazy. All right. And I look at this and my eyeballs almost jump out of my head because look, 252 times 2 would be 504. So the rate equals 1 gallon per 2 infant days. Oh my goodness. That is lovely, isn't it? I like it so much. Okay, and then we're trying to find out, then step 2 is we use the rate to answer the question. And the question is, if we get more kids and more milk, how long would the milk last now? Now, here's the part of this question that drives me crazy. Have these kids already been drinking these gallons of milk? Or are we putting everybody together and setting this experiment up? The latter is what we're supposed to assume. We're supposed to assume that we just know this, but now we're adding in more kids and we're adding in more milk, and we're gonna calculate the new time based on all that. That's confusing to me. I just imagine this room full of babies with bottles. It's whacking me out. Okay, so we've got our rate. So now we want to use this, and we're solving for the number of days, right? So the rate is 1 gallon for every 2 infant days. And we're going to multiply that times the number of days, which we don't know. And then we're going to multiply that by the number of infants, which is 42 plus 14 more infants. There's no denominator to this. I'm just writing the word underneath to save myself some space. And that is going to equal, how many gallons do we have in all now? 300 gallons, right? If we add it together, equals, I can write it separately, 252 plus 48 gallons. Is your head spinning? Mine is a little. All right, beautiful. So now what I'm gonna do is I'm going to squish this together because these are all being multiplied, right? So I'm gonna write 42 plus 14 is 56 times 1, 56 infant gallons. Again, this doesn't make sense, I'm just tracking my units, over 2 infant days, right? Because that's what I had there. I like the slash better, that makes more sense to me. This whole thing times D equals 300 gallons. All right, infant cancels top and bottom. I multiply by the reciprocal, so 2 days over 56 gallons. I multiply on that side, then I'm gonna do the same thing, but I'll just do it down here. D equals 300 gallons, that's what I already have there, times 2 days over 56 gallons. The gallons cancel, and I get that the number of days is equal to, and honestly, this would be enough for the answer. The number of days equals 600 divided by 56 days, right? Because my gallons canceled. And this I could take down to what? I could at least do 300 over 28. I could do 150 over 14. I could do 75 over 7. John takes it out. I like 75 over 7. That's a nice final answer. John shows it. Let me just show you. We have 300 times 2 divided by 56. He has that as well, 300 times 2 divided by 56. And then he goes to the decimal number, which is a little bit over 10. And I like this because I can see that that would be a little over 10. 10 would be 70 over 7. So this is a lovely answer. And right here, John also had this exactly. Getting the final form of the answer is not what's important to me. Being able to manipulate these equations is more than enough of a challenge. So that is the end of lesson 25. I very much hope you enjoyed it. I very much hope it made some inkling of sense to you. And I will see you for lesson 26.